In this lecture, I usually start by asking, does anybody know what the most watched episode of which show, that's a terrible way to say it, which show's episode had the highest viewership in history? That's a better way to say it. And it's a little bit of trivia. I remember this showing up in Trivial Pursuit a time or two, and we would talk about it. There were guesses that would come out and so on. And rarely do people guess it correctly. Sometimes, every so often, I get somebody who knows. And from our book, we see that the answer is MASH, specifically the final episode of MASH. And it says that there were 50 million households watching that last episode, approximately 60.2% of the viewing population in the United States. I remember watching that episode. It was rather emotional and kind of surprised me how much my mom was crying during it. Later, I've watched it and realized why it was so emotional, but regardless, a lot of people watched it. Now, I also don't remember people calling my house or stopping by and saying, hey, did you watch that episode? It's just not something that they do. And so you have to ask, how do they know that 50 million people watched that episode? Nowadays, they may have some means in place for finding out where their data are going, because so much that we do now is through the internet. But in 1983, we were watching with an antenna. Perhaps we had cable, but often we watched with an antenna, which meant that the broadcasters were just sending the information out into the world. And if you had an antenna and a TV, you could receive that signal and then watch the show. And so it wasn't something that they could ever track. Well, it turns out that what they do is they take a survey. They talk to a certain number of people. Maybe they talk to 5,000 people and ask them, did you watch that last episode? That's enough data that it would be a lot, but not as overwhelming as asking 300 million people, did you watch MASH? And so with that in mind, they can then take that small collection of data and say, well, 60% of this population watched it, so we think 60% of the entire population must have watched it. Of course, there are some requirements in place with that data set that have to be there in order for you to accurately extrapolate to the entire population. And that specifically, one of those requirements is that it must be a random sample. A random sample, as you see on the screen, is a sample that we get when every element or every person in the population has an equal chance of being selected. That means if we want to run this test, we're not going to go down to Walmart and ask everybody in Walmart if they watched a particular episode, because not everybody shops at Walmart. We have limited the population to only those people at Walmart. We, by the same token, would not go to any store and ask. We wouldn't necessarily call the last 20 pages in the phone book. While that might be a large number, it won't be it won't be a random sample. We've limited it to the end of the alphabet. And so you need to make sure that your sample is entirely random in order to be able to truly extrapolate it. Now, if you wanted to find out how CWI students feel about a particular thing, then yes, you can focus in on CWI students. But again, you wouldn't stand at the east door in NCAB, NAMPA's campus academic building, and only talk to the students who walk through that door, because not everybody attends class in that building. You would have to randomly select students and send an email to them or something, or maybe call them. That way it is entirely random. So here I put a sample problem on the screen. We've got some hotel owners in a large city interested in how the city's citizens feel about casino gambling. And then it asks which of the following would be an appropriate way to select a random sample. The first option is to pick those who live in oceanfront condominiums in the city. Now that it's a random survey, it says, but you've limited it to the people only living in those condos. Maybe the first 200 people whose names appear in the phone book, well, that's the same thing as the 200 at the end. So that's not entirely random. But the third one, randomly select neighborhoods of the city and then randomly survey people within the neighborhoods. It's entirely random at that point, and everybody has an equal chance of being selected. So option C would be the one that makes it a random sample, which means once you collect your data, you could extrapolate it to talk about the entire population with that same information. And so now let's talk about ways that we can show data. We may collect quite a few bits of data, like here on the screen. I've got a bunch of numbers that actually represent the ages at which boys went through a growth spurt. And if I remember correctly, there are 35 boys here. And so that's a lot of information. We need to have a good way to represent those numbers so that they make sense. Well, looking at my data here, I see that I've got a 10, and that's the lowest number. All of these are 2-digit numbers, and they all start with 1. So 10 is the lowest. Now I'm looking to see if there are any 19s. I see an 18 here. I don't see any 19s though. So all of these ages go from 10 to 18. So maybe what I'll do is I'll write those ages down in a column here. And I am going to figure out how many of each of these numbers exist within this data set. Now I do have the option saying, well, I'm looking for 10s and go through and find all the 10s. There's one. Do I see any others? Nope. So there's only one of those. How many 11s? That would work unless I accidentally skipped a number and all of a sudden I'm in trouble. And so what I recommend you do, just because you're less likely to make mistakes this way, is to start at the first number. That's a 12. And so I'm going to put a tally mark by the 12s. And then the next number is a 14, followed by a 13, then another 14, then a 16. And you can see by doing it this way, I will definitely get every number that is here. And that will be more accurate representation of the data. I'm less likely, I think, to make a mistake. So I would go through this entire data set bit by bit. And unfortunately, you're probably taking the exam online, which means you won't have the ability to write on the test paper and just cross things out. So hopefully we can find a way that works for you so that you can get these data best organized. I'm going to go ahead and finish putting all of this together so that we can see how many of these young men reached their growth spurts at these various ages. We probably all had an idea of what age we expected a young man to go through his growth spurt. And so we'll see if this collection of data matches what you had in mind. I asked my face-to-face class the other day what they thought, and they said 12 to 13. That was what they expected. And as it turns out, now that I've done all of that, we can see that there were more who went through their growth spurt at the age of 14 than any other age. Though 13 and 15 were pretty close, 14 had the most. When we do this sort of showing of the data, we call it a frequency distribution. Frequency meaning how often does a score happen, and distribution is how are the numbers distributed among those ages, I'm going to say, though it's any characteristic you're looking at. So now I've created a frequency distribution. And we could, at this point, rather than have tally marks, we could write the numbers down. Maybe change color here. So we have 1 of those, 2 of those, 5 12s, 7 13s, 9 14s, 6 15s, 3 16s, 1 17, and 1 18. And so they may even put this as a table with, say, I'm going to go ahead and age and then frequency. Frequency is how often that number showed up, and age is, of course, in this case, the age of those young men. So we've got frequency and age. That's our frequency distribution. If we were to grab that distribution with the tally marks, notice the 14, though, because there are so many tally marks, it extends further to the right. 13 and 15 extend just a little less to the right, and so on. So if we rotate this vertically, I shouldn't say we rotate it vertically, we rotate it 90 degrees to the left, maybe we could do the same sort of thing, but now the ages are going to be along the bottom. And we will show the height of a bar above those ages, and that would be the frequency. So maybe this is a frequency of 10. Oh, that should probably be a 5, though. So that'll be a frequency of 5, because we don't have frequencies above 10. So that would be a frequency of 10. And then we could say, well, 10-year-old boys, there were 1 of them. So we're going to put a bar that's 1 unit tall. There were 2 11s. So we're going to put a bar that's 2 units tall above the 11. There were 5 12s. So we'll create a bar that's 5 units tall for 12. There were 7 13s. So we'll create that bar. 14s, we've already said there were 9 of those. So we'll create that bar. 15 had 6. So that would be smaller than the bar on the 13s. There were 3 16s and 1 each of 17s and 18s. And so now, very quickly, you can see how these numbers are distributed. And sometimes they will write the frequency above the bar. So it's very clear how tall that is. It's more clear than making you read it on the chart. This is called a histogram, and it portrays the exact same information that we had in the frequency distribution. We just made more of a picture out of it. So with this histogram, we can see that there are 9 14-year-olds that went through their growth spurt. We can see that there are 3 16-year-olds. And notice I don't have to go back to the original data now. And if I were to ask you how many 16s at the very start, you could go through and count the 16s. And you probably would have counted all of them, but maybe you would have missed one, maybe you would have accidentally counted one twice. Mistakes can be made when we have just a big set of teen numbers. But once we have those organized, it's far more clear what information we're looking at. And this will also help us later in section 12.2 when we're talking about measures of central tendency. Notice kind of the middle of all of these data is about 14. That's the tallest bar. Everything seems to fall away from that on the left and right side. And so it's a really good way to represent data. Now, not all data will be represented this way in a good fashion. There are others that maybe wouldn't be represented so well. Oh, I just remembered that one of the things that we will sometimes do instead of a histogram is we will connect the middle of the top of each bar together with a line and make a line graph. They call it a polygon chart. And it's just a line graph. We've dealt with line graphs before in class, but you may have something like that that shows, again, the same information. Just however you feel best portraying that information is which chart you're going to use, whether a frequency distribution with tally marks or a frequency distribution with the score, the age, and the frequency as a number, or maybe a histogram or this polygon chart. Those ways are all different ways to portray data. But like I said, not all data fit really well in this sort of frequency. For example, here I've got a selection of test scores. And we can see that we have, I believe it's 40 different test scores there. And not many are duplicates. And so rather than, let's see, what's the smallest number here? We've got a 47, the largest number, 94. I don't know that those are the largest, but it's pretty close to the largest and the smallest. Well, there's a 45. Regardless, mid 40s to mid 90s, that's 50 different numbers we would have to put down in that column. And a lot of them would only have one score that fit within that. So it doesn't make a lot of sense to do the distribution that we just saw. However, these are test scores. And one of the things that we do in class is we assign grades. And the grades are based on your test score and where that fits within a range. So maybe I would rearrange this data set and we'll look at the 40 to 49 scores and the 50 to 59 scores. So now this fits better with the way we assign grades. Because as we said at the start of the semester, I grade on what I call the 90, 80, 70 method. Anything in the 90s is an A, anything in the 80s is a B, 70s is a C, and so on. And so this fits really well with that sort of distribution. And I'll make some tally marks again. We've got an 82, we've got a 47, we've got a 75, 64, 57. And in class, I have a student come up and cross these out. So, because it takes a little while, we've got 40 tally marks to put on here, but it will give us a good sense for how many got which grade on this particular test. I mean, we expect a certain percentage. I don't know who wrote this test, but they should have an idea for how many students they expect to pass the test. We'd all like all students to pass the test. It just doesn't seem to happen usually. But once we are done pulling this together, we'll have a good sense for how the students did. And that, to me, as a teacher, is really important. I really want to know not just that my students are doing well, but how many of them are doing well, how many are not doing well, so that I can perhaps modify my instruction to reach more students. That's really the purpose for me behind gathering data like these. I want to know how I can do a better job. I'm just about done here. Looks like we have a pretty even distribution, though we have more 70s than anything. Quite a few 80s. So there were a bunch of C's and quite a few B's, some A's, some D's, and a number of F's. It's a pretty decent distribution, I guess, if you're looking for most of the students to be in the middle. But notice this isn't just a frequency distribution, so we call it something else. We call it a grouped frequency distribution because we grouped the scores into what we call classes. So each of these is a class. Now you will be asked in the homework to define the class width. To find the class width, we're really looking at how many scores fit within any given class. So what we're going to do is we're going to take the high score in one class and subtract from it the high score in the class next to it. So 79 minus 69, and we end up with 10. So the class width in this example is 10. You just take, or we could do the lower limit in each class. We could have done 70 minus 60, but that would have given us the same class width. And that also highlights that if you're making a group frequency distribution, you have to make sure that those classes are the same size. We wouldn't do 40 to 45, and then 46 to 70, and then 71 to 74. That just wouldn't give you enough information. It would be kind of silly almost to do that sort of distribution. It just wouldn't give you enough to know what was happening. And so now we have this grouped frequency distribution, and we can see how students did on the test. If a D is passing, then it looks like the vast majority passed this exam. If a C is passing, it looks like more than half did at least, or right about, yeah, a little more than half passed the test. It's up then to the instructor to decide whether that's what they expect to see, what they want to see, and if anything else needs to be done. One of the things that this does for me, though, not only help me see how they're passing, but it also gives me a little consternation because, well, how close were they to getting a higher grade? If I have 11 70s there, but were they low 70s or high 70s? If they're high 70s, then maybe I can make a minor change and all of a sudden a bunch of those become Bs. If they're low 70s, I may need to work a little harder if I want them to become Bs. But I need to know how that distribution would work. And so what I might do is create what's called a stem and leaf plot. You know, maybe I should do this down below next to the other one so we can see that we will get a similar shape to the curve. That can be really useful. With the stem and leaf plot, we're going to have a stem and leaves, oddly enough. The stem are the digits in the tens place. And the leaves are from the ones place. Notice I can say that because these are all two-digit numbers. If they weren't two-digit numbers, we would have to modify things a bit so that it made sense. So I'm going to write down the tens places. We had the 40s, the 50s, the 60s, 70s, 80s, and 90s. And then I'm going to create a vertical line to separate the stem from the leaves. And now, once again, I'm going to change colors here because I'm going to be crossing out the numbers again. I'm going to go through and write these out, but it's a little different. This first number is an 82. So next in the 80s, I'm going to write a 2. So the stem was 8, the leaf was 2 for a number of 82. The next number is a 47, so in the 40s, I'll write a 7, then a 75, then a 64, then a 57. So we're getting the same information as we had before regarding how many were in each class, but now we also have what exactly was their score, and so we get distribution within a particular class. And that gives even more information than we got from the grouped frequency curve. So as a teacher, I would probably rather have a stem and leaf plot of my students' work on the exam, so that now I have a sense for not only how many passed, but how closely they were to the border. If I have a bunch of, let's say 70 is passing, and I have a bunch of students who got 70, 71, or 72, then I know they barely passed, and I want to help prevent that in the future. With 40 numbers, this is going to take a little while, but it's worth it when you're analyzing the data. On your homework and on the exam, you won't see this many at all. I just do this one in class and therefore here on the video so that you can see that it works well and gives us a good sense of the information involved. I just remembered I'm going to want to open my homework and show you a couple of tips from there as well. So I hope I don't forget that. And I'm almost, oh, that's not an 88, that was an 84. See, that's the kind of mistake one might make. A 59 and a 76. I hope I didn't make that mistake somewhere else. But we can see that the number of leaves in the 50s and the number of leaves in the 60s matches what we had in our group frequency of 6 each. There were 11 70s, and so those are all listed out, and there were 9 80s. Now let's look at some of those. Those 9 80s, only 2 of them, 88 and 87, were above 85. That suggests to me that most of the 9 tests, most of those 9, just barely got in the B range. It's going to take a little more work to get those students up to an A than it will for the 88 and the 87. If we look in the 70s, at 5, 6, 7, there's a 9, 6, 8. A bunch of those were 5 or higher. So they're getting pretty close to getting a B. In the 60s, which would be a D, looks like 4 of the 6, so 2/3 of them were above 5. There's a good chance I could get those students up to the C range with a little bit of work. So now I have even more information than how many scored in a particular grade, and I know where they were within that grade. So a stem and leaf plot becomes quite useful there. Like I say, on the homework and the exam, you won't have so many data points to look at because it takes too long. But I'll show you also pretty soon a trick that will make that go a little bit faster. We end section 12.1 talking about ways that data might be presented which could be considered deceptive. Both of these charts portray the exact same data, the table in the middle. That table in the middle tells us the poverty rate for a given year. Now notice the chart or the graph on the left makes it look like, oh my gosh, it grew way fast. And the chart on the right says, oh, well, it didn't grow all that fast. It grew, but it's not crazy. And so if you want to portray a particular emotion, If you want people to think it grew really fast, you would show the left-hand chart. If you want people to feel like it grew, but not very quickly, you would show the right-hand chart. They both show the same thing. So we have to watch the charts and see what they're talking about. Notice the axis here goes from 11.3% up to 12.9, the difference of only 1.6%. Whereas the axis on the other goes from 11% to 19%. So maybe you will show a smaller range on the y-axis to give you a greater slope, a greater change in value. Or maybe you'll stretch that axis out so that it looks like a smaller change in slope. Because remember, slope is rise over run. So rising a little bit on the left-hand chart looks bigger than it does on the right-hand chart. A couple of things there to watch out for. Maybe they will show you a graph like this, the purchasing power of the diminishing dollar. Using a word like diminishing makes me feel a certain way. Oh, this is something I need to watch out for. And it starts with a dollar is worth $1 in 1980, and in 2005, it's only worth 43 cents. But look at the area of the dollar itself. We remember how we talked about area was length times width. It not only got shorter, but it got skinnier. So if I'm looking at the, oh, I just did something weird here. If I look at my table, I can see that it was worth $1.43 is just under half. And so it is just under half as tall, but it's also a lot skinnier. I could probably fit 4 of these little dollars into the big one, almost like the dollar is only a quarter of what it really is worth. And so by shrinking it, its width as well as its height, they've made it feel even smaller than it really is. Had they kept the width and just cut it off when it reached the value, then it would perhaps be a more accurate representation. Also notice the x-axis, 1980 to 1990, that's 10 years, to 95, well, that's only 5 years. It's 2000, that's 5 more, and 2005 is 5 more, so they changed the axis. I don't know why they went to 5-year differences. Maybe 1985 had a great big dollar up here, and it didn't show this rapid diminishment. And so watch for things like that. What do they do with the axes? Did they change how quickly the axis changed to show something else? Here's another example. They're talking about the number of square feet in an average US single family home. And looking at the shadows, oh my gosh, that grew huge. It got really big. But look at the values associated with those. 1740 up to 2392. That's an increase of 652 square feet, which is about a third of this. So they would have had to add only that much of the shadow to it to be an accurate representation, but instead they made the new shadow really big. And it looks like maybe 4 times as big, even though it only increased by a third as much. So it was a 30% increase, but the shadow was a 400% increase. Again, we can look at the years down in the bottom. Oh, down here, 1980, 90, that's 10 years. And then they jumped to 2010. What happened to 2000? What were houses like then? Was it the same size and they didn't want to show that? Or was it bigger? Though I can't imagine them wanting to show that. We don't know. But we know that things aren't drawn exactly the way they should be. So those are all things to watch out for, and that covers section 12.1. You'll be asked about potential deception in graphs when you're in your homework. So in 12.2, we're talking about measures of central tendency. And generally speaking, when we say measures of central tendency, we are talking about averages. Now, when we were younger, we were told that to take an average, you add up all the numbers and divide by the number of numbers. And that's true for a particular type of average. Average is actually a very general, and it means kind of, oh, it's almost like I don't know how to spell. It means the middle of your data. So if you want to get specific, which we do in this section, we will see 4 types of average. We will see the mean, we will see the median, we will see a mode, and we will see mid-range. Those are ways for us to find the middle of our data set. Now, the mean is what you were taught for average. Add the numbers, and I'm going to use scores, though it could be any set of numbers, and divide by the number of scores. Now we denote this, or we write it this way. The sum of the scores divided by the number of scores. So I used this symbol. Oh, that's not a very good representation. It's like a stylized E. It is the Greek letter sigma, capital sigma, and it means sum of. So add all the things together that are right next to it. So we're summing X, which are the scores. N is the number of scores. So add the scores, which are X's, and then divide it by the number of scores, which is N. The median is the middle number, or the middle score, when they're ordered numerically. Now, if you have an odd number of scores, it's the middle number. If you have an even number of scores, it's the mean of the middle two. So if we had 6 scores, you could have 3 at the bottom edge, 3 at the top. There isn't a middle. And so we'll take number 3 and number 4, add those together and divide by 2. And that will be the median. The mode is the score that shows up most often. And if you have a frequency distribution, it's the highest frequency. So I'll write that down. Now, there may be multiple modes. There may be no mode. So if you have no score that shows up more often than any other, there's no mode. Like with those test scores, I don't think we duplicated any of those. Maybe we did. With our previous frequency distribution, we had maybe 7 3s. And so that appeared most often and would be our mode. Mid-range is the mean of the largest and smallest numbers. So you'll add the largest number or highest score to the smallest number or lowest score and divide those by 2. That will give you the mid-range. So we've got mean, median, mode, and mid-range. Now let's look at some problems and calculate these. Here we've got 5 employees in a television manufacturing company who earn these salaries. We need to find the median salary. That's part A. And so it says of the 6 people. So the 5 employees and the manager. So let's get the smallest number here. We need to put these in numerical order. I should probably say ascending order. The next highest, oh, they're already in order for me. That's nice. Then 21,500, then 22,600, then 23,000, then 95,000. So we have 6 numbers. The median is the middle number. And since it's even, we're going to take those 2 and find the mean of those 2. So we'll take 21,500. We'll add that to 22,600. And we'll divide by 2. Let me grab my calculator. So 21,500 plus 22,600 is 44,100. Divide that by 2 would be 22,050. So that would be our median. Oops. Often it is one of the numbers we've been given. But in this case, because we have an even number of numbers, it's the mean of the middle 2. Now, for part B, we need to find the mean. So we need to add all of those together. And we will divide that by 6 because there are 6 numbers here. Now that 95,000 is so much higher than the others that it's going to skew our result a little bit. And that's fine. That's how this works. We just know not to expect it to be about 22,000 like our median. And that's why when I hand a test back, I like to not only tell you what the mean is, but also the median. Adding all of those and dividing by 6 gives me 33,700, which is higher than even the highest employee salary. And it's because of that 95,000 for the manager. That really changed the mean. So if I were to hand a test back and I said the mean was 86, but the median was 70, remember the median's the middle number, so half the scores are above that and half are below. So half the scores were above 70 and half were below 70. But the mean was 86. That means we had quite a few scores above 86, like a few hundreds, that could really raise that mean up. So if you have both of those data points, the mean and the median, now you understand how the scores are distributed a bit more. Whereas if I just told you the median or just told you the mean, you might feel either bothered or excited by what you're hearing. If I told you a mean was 86 and you got an 84, you would think, oh, I got below the mean, I got below the average. All these students did way better than I did. But if I tell you the median was 70, well, your 84 is well above that 70, so you're in the top half of the class. You're not as high as those few that raised the mean, but you're in the top half of the class. So that can be really useful to know. Now let's look at some other averages. Here we are calculating the mean, median, mode, and mid-range with this data set. Now I want to show you something that I think will be helpful. I have found that a number of calculators have it built in so that you can calculate this information and let the calculator do most of the work. You just have to enter the data. Now I'm going to again, this is a TI-30XS. I also have a TI-36 Pro that has the same feature. I looked at another calculator. Let's see, there's a Casio that has this. Lots of them do. You just have to find how to enter it. I'm going to click data, and it brings up these lists. There's list 1, list 2, and so on. And so I'm going to list those scores. There's a 52, there's a 69, there's a 75, there's an 86, another 86, and a 92. So I've got all the data listed now. Notice right above the data button, it says stat. So I'm going to click second to get the green stuff and click data. I want one variable statistics, so I'm just going to hit enter. And it asks me where the data are located. They're in list 1, that's where I entered them. So I'll hit enter. And then it comes down to the frequency. Now the frequency is just 1, so I'm going to slide over to the 1 and hit enter. And then it'll say, okay, do you want me to calculate that? I'll say yes. Now notice, it says n is 6, so the number of numbers is 6. Right below that is x bar. X bar is the mean. And so the mean of this data set is 76.67. I rounded it, but you know how to round, so that would be fine. The number below that, the SX, is standard deviation. And we talk about that in 12.3, so we won't worry about that right now. Below that is sigma x. Now that's lowercase sigma. That also is a standard deviation. Again, that would be tomorrow's lecture, so we won't worry about that right now, but just know that those are there. Here's that sum, the capital sigma x, so that's the sum of all the numbers. Here are the sum of the numbers squared, and we won't worry about that right now, but that is used in other calculations. Gives you the minimum number. First quartile, the median, 80.5, that's one we need to know. So that will give us our median. The third quartile and the max. We're not going to deal with all of those today, but we've got our median, 80.5, and our mean, which is 76.67. Those are two of the things we needed. We needed 76.67 for the mean, and the median, it said, was 80 point something, right? Let's see. Median was 80.5. So we got both of those just from that calculator's calculation. Mode is the number that shows up most often, and we have 2 86s. No other number is duplicated, so the mode is 86. And then it asks for mid-range, and that's the mean of the largest and smallest. So we'll take 92, add the smallest to that, which is 52, and divide by 2. And 92 plus 50 is 144. Divide that by 2 is 72. So the mid-range is 72. The mode is 86. The median is 80.5, and the mean is 76.67. So with the data set, we can pretty quickly calculate all of this. Now we could have done that by hand, added all the numbers and divided by 6. That would give us the mean. The median would be, because there are 6 numbers, it would be the mean of the middle 2. The mode we would calculate the same, and the mid-range the same. I just wanted to show you that you may have a calculator that will do a lot of this work. And that's extremely useful if you have a large data set, like this grouped frequency, or it's a frequency distribution, not a grouped frequency. So here we have 151 data points. We have 2 zeros, we have 1 1. And again, rather than writing all that out, 2 zeros, 1 1, we have 3 2s, we have 12 3s. I'm not going to write all of those down, but you can see this would get really crazy if we wrote all of those out. So rather than do that, we use a group or a frequency distribution. You know, I should have left some of those. Let me put some of those back. Oh, it won't do it automatically. Okay, so we've got 2 zeros, we've got a 1, we've got 3 2s. Oops. So if I were adding these together, 2 zeros add to 0, plus 1, there's 1 1. 3 2s would be 6. And we get that by multiplying the number of numbers by the score. So really, they're just multiplying the frequency by the score. And then we can add all of those together and divide by the number of numbers. Now, this particular problem has already told us that the number of numbers is 151. 0 times 2 is 0. 1 times 1 is 1. 2 times 3 is 6. 12 times 3 is 36. 4 times 16 is 64. 18 times 5 is 90. 13 times 6 is 78. 31 times 7 is 217. That's getting big. 8 times 26 is 208. I'm doing these in my head, so hopefully they're right. 15 times 9 is 135. 14 times 10 is 140. And now we could add all of those together and divide it by the number of numbers. Now, to get the number of numbers, if they don't tell you that 151 is how many numbers we have, we would add our frequencies. The frequencies are the number of numbers. And so to find the mean here, which is X bar, that's the mean, we could sum all of the scores times the frequencies and divide it by the sum of the frequencies. That will give you the mean in a distribution, a frequency distribution. That works really well. Again, I'm going to bring up my calculator because, like I said, this will do all of that work. So I'm going to hit the data button, but twice, and that allows me to clear it. I'm going to hit the up arrow, and it goes to clear all. That's what I want. Now, in this first column, I'm going to enter the scores. Those are 0, 1, 2, 3, all the way up to 10. Then I'm going to hit the right arrow to go into list 2, and I'm going to enter frequencies here. And if I don't enter the frequencies right, remember at the end when it tells you how many numbers there are, if we don't get the 151 that they told us, then we know I made a mistake. All right, now I need to get into the stat. So I'll hit second data to get into stat. I need the one variable statistics. The data are in list 1, so I'll just hit enter. The frequency is in list 2, so I'm going to hit that. And now when I calculate, it calculates the number of numbers is 151. The mean is 6.46. So let me write that down. Bring that calculator back up. Again, standard deviation, we won't worry about that today. The sum of the numbers is 975. That's what we would get if we summed all of these numbers times the frequencies, divide by the sum of the frequencies, that's our number of numbers. So if we take 975 and divide it by 1, we get our 6.46. And so the calculator has all of those bits and pieces in it if you run through those steps. The median, it tells me, is 7. Now, how would I find that if I only had this table and didn't use the calculator? Remember, we said the position of the median is n plus 1 divided by 2. N is 151. Add 1 to that, divide by 2. So 152 divided by 2 is 76. So I need the 76th number. Now that I can find just by adding frequencies. 14 plus 15 is 29, plus 26 is 55. Now I need to get to 76. I'm at 55, so I need another 21. And that occurs partway through this one, so the score that is associated with that position is 7. And that matches what my calculator gave. So that is how we will find the position of the median when we have this many numbers. You don't have to count over 76 numbers. You can count frequency, which are the number of numbers. When you find the right position, you read the score that goes with that. And that will give you the median. Now the mode is the one that occurs most often. One that occurs most often is the one with the highest frequency. 31 is the highest frequency, so the score associated with that is 7. So the mode is a 7 because there are 31 sevens in this data set. The mid-range is found by taking the highest score, adding to it the lowest score and dividing by 2, and we get a 5. So 5 is in the middle between the lowest and the highest. The median and mode are both 7s. The mean is a little below that at about 6.5. So now we have a better understanding of this entire data set using a frequency distribution to understand how the data are spread out, and then calculating the mean, median, mode, and mid-range, which are measures of central tendency, basically the numbers towards the middle of the data set. I hope this has helped. We've only covered 2 sections here. I'll need to make another video to cover section 12.3, which are the standard deviations. So watch for that, but this will get us started. Let me know if you have questions.